Hello everyone, welcome to this lesson. So in this lesson, we're going to continue our discussion on curve fitting. In the previous lesson, we went through linear regression, that if you have a set of data points that have a linear trend to it, how can you fit a model to it? How can you fit an equation to it? And we found that the best fit to these data points is defined in terms of the line that would minimize the sum of the square of the residuals, right? And we defined what a residual is. A residual is basically the distance between the measured value, which is basically the data points that you have, and the model. If you can minimize the distance between the measured value and the predicted value of the model, you have the best fit, right? So right now, what if you don't have data points that follow a linear trend? What if they follow maybe a curve trend? Well, a curve trend can be either one of two things. It can either be a polynomial trend, right? Or it can be either, a more complex function like a exponential or power function or a logarithmic function, right? So in this lesson, we're going to deal with if the pattern is a polynomial pattern, how can we fit a model to it? And this is called polynomial regression. The previous lesson is also called polynomial regression, but is usually defined in a class on its own as linear regression. And polynomial regression is basically anything that is second order polynomial or larger. Okay. Now we're going to go through the theory behind the method, then we're going to go into the code and see how the code changes, in comparison to a linear regression. Now, as we said in the previous lesson, the best fit is the line that minimizes the sum of the square of the residuals. Now, let's actually look at this. And the model in this case is going to be a second order model. Now, a linear order stopped here. It was a0 plus a1 xi. And in this case, since we're doing a second order polynomial, it's going to be an a2 xi squared. So we're going to add this extra term. Now again, since we're doing optimization here, we're going to be getting our critical points, and our critical points are basically where our derivative is equal to 0. Since the SR depends on three variables here, A0, A1, and A2, we're going to have to get a partial for each one of them. Now the partial in terms of A0 is here is going to be -2 multiplied by this sum here. Right now, when we do the partial in terms of a1, we come up with this xi, okay? And when we do the partial in a2, in addition to the sum that we have here that is multiplied by -2, we have this xi squared. Okay, now by distributing the sum inside of here and rearranging partially, this is the equation for the first one, this is going to be the equation for the second one, and this is going to be the equation for the third one. So by doing this, we came up with three equations and we're seeking three unknowns, A0, A1, and A2. So basically, we ended up with a 3x3 matrix. Now let's look a little bit closer at the matrix. Now the matrix is defined in terms of the data points, much like the two equations that we derived in the linear regression were defined only in the data points. We find that it's defined in terms of n, which is the number of data points that we have. In this case, we have 20, and is defined in terms of the sum of all the x points, and also the same sum we have down here. We have the sum of xi squared. We also have the same sum here and here. The sum of xi cubed, we have it here as well, and the sum of xi to the fourth. Okay, we also have those three sums here, the sum of all the y points, xi multiplied by yi, all summed, and also xi squared multiplied by yi, all summed. Okay, so from this case, you can see that for us to actually solve the system of equations, we need to find the matrix A, right, the coefficient matrix A, and we need to find the vector B, which are the points on the right-hand side, right? So in curve fitting, you can find from polynomial regression, it's kind of like an intersection between optimization, curve fitting, and solving systems of equations, right? We used optimization to come up with these three equations, and also we're going to use these points to come up with the matrix A and B, and we're going to apply what we learned from solving systems of equations to find what are the solutions A0, A1, and A2. Okay, so that's the entire theory behind going forward to polynomial regression. When we dealt with linear regression, we only had two equations. We went to polynomial second order. Now we have three equations that we have to actually apply systems of equation techniques to find what are solutions, which are A0, A1, and A2. So let's actually go ahead and go into the code. Now there's a lot going on here in terms of the code, but the reason I use those apostrophes is because I want you to see that there's only one part of the code that is new for you here. Everything else you actually already know. Now, as I mentioned in the previous lesson, we were going to generate a general polynomial regression program, which means a program that can deal with any order polynomial, second, fourth, sixth, eighth, whichever you would prefer. Now, the first thing I'm going to do is I'm actually identify the data points and the order, and this is basically the reason I separated them up here, because that's the two things that you're going to be changing depending on what you're dealing with. Sometimes you have 20 data points, sometimes you have 30, 50, 100, and also sometimes you're seeking another order. So N is for number of data points, and O is for the order. In this case, we're writing a program for a second order. Now, in previous lessons, we dealt with the dim keyword. The dim keyword is basically it dimensionalizes our arrays, right? Now, in this case, since we're going to be changing the N and the O, and we're going to be making this a general program, I'm going to have to use another keyword. It's called redimensionalize, redim function. And this is basically where you begin to add a variable when you're dimensionalizing these, as you're going to see here. So let's go ahead and see this a little bit closer. So say I'm dealing with a second order polynomial. So when you're using a redim, it's going to be A is equal to 1 to 2 plus 1, so 1 to 3, which means I'm telling it I'm going to have 3 rows, okay? And it's going to be also 1 to 3 here. So I'm basically creating a 3 by 3 matrix, which is basically what you would create with a second order polynomial. Now, what about the B vector, the points on the right-hand side here? Well, basically, we're also going to have 3 numbers. So it's going to be B is equal to 1 to the order plus 1, so 2 plus 1, so 1 to 3. And this is X and Y. This is basically just the points that I have, and they're going to be 1 to N, and in this case, there's going to be 1 to 20. And the last thing is, we also need to create a vector for our solutions, right? And I just called it S. And also it's going to be 1 to the order plus 1. So we're going to have 3 solutions, right? So if I'm dealing with a second order polynomial, I should have 3 solutions. Fourth order, I should have a third order, I should have 4 solutions, and so on. So like what we did with the linear, the first thing I need to do is I need to input the X and Y points. And this is a very simple loop that will do that for you and is related to these cells to input these values. Now, here is the meat of this lesson. And this is, by understanding this code, you will be understanding all of what you need to understand in terms of coding in this lesson. Because if you look down here, this is after I create A and B, I can just enact a technique that I learned in previous lesson, right? The solving a system of equation using, in this case, naive Gauss elimination. And given that I have solved it and have A0, A1, and A2, that means I have created the line that best fits these data points. But also I need to know what is the effectiveness of that model, which means I need to go ahead and calculate my R squared. And this is just the display code that displays my answers here. Okay, so let's actually go through the main part of the code that you need to learn, which is creating matrix A and B. So the first thing is the outer loop. We have for I is equal to 1 to the order plus 1, so 1, 2, 3. So which means I'm dealing with 3 rows. So let's actually go through all of it, all of the loops, because there's a lot going on here. Let's see, for I is equal to 1 to 1. So let's assume for I is when I is equal to 1. So 1 to 1, that means this is only going to loop once. So K is going to be equal to 1 plus 1, which is 2, 2 minus 2, which is 0, so K is 0. So when K is 0, let's see what's going to happen with this loop. This is a simple sum loop. So when K is 0, this is just going to be 1. So this is going to be just adding 1, 1, 1, n number of times, which means 20 times, which means when I is 1 and J is 1, this loop is going to create the number 20, right? And this is basically is going to create n, right? So then after it creates the sum, is going to say A11 is equal to sum, and A11 here is equal to sum. Now, why this is ij and this is ji is going to make sense as we move on through other loops. So now, by going through this one loop of the j, we created this one, A11. So let's actually go to the second. So let's actually go down here. For L is equal to 1 to n, so this is going to loop 20 times. And for this sum, I is 1, right? So 1 minus 1 is 0. So this is 0. And what's remaining is this I. So this is going to loop and is going to sum all the y. And it's going to be B1 is equal to sum. So by going through one loop of all of this, we have created this n, A11, and created this sum of y, B1. So let's actually go see what is the second loop of the I is going to do. So I is equal to 2. So this is j is equal 1 to 2. This is going to loop twice. So for the first j, that's going to be 2 plus 1. So that's 3. 3 minus 2, that's k equal 1. So when k equal 1 for this loop, that means it's going to create a sum for the x. So when it creates a sum for the x, that's going to be A21 is equal to sum, and A12 is equal to sum of all the x's, which means I created the sum of the x set here, A12 and A21. Okay, so let's actually go ahead to the second j. So the second j is j equal 2. So that's 2 plus 2, that's 4. 4 minus 2, that's 2. So that means k is equal to 2. So this is going to create the xi squared sum, right? And when it does that, A22 is equal to sum, and A22 is equal to sum. So we created this sum here at A22. Okay, and now we're done with this loop. We go here, and now j is equal to 2, which means 2 minus 1 is 1. So that's going to create the y multiplied by x sum, which means it's going to create this. So B2 is equal to sum. So now my second loop of the I, what did it create? It created this sum of x and sum of x. It also created this sum of xi squared, and also created the sum of yi xi. Okay, so let's actually go ahead to the third I. So j is equal to 1 to 3, so that means this is going to loop 3 times. So let's see what it's going to do for the first loop. So k is equal to 3 plus 1, that's 4. 4 minus 2, that's 2. So now this is squared. So this is going to create the xi squared sum again, right? But this time is going to be A31 is going to be equal to sum, and A13. So 31. So where is 31? 31 is this, and 13 is that. So now we created the sum of xi squared here, and sum of xy squared here. Okay, so let's go to the second loop of the j. So it's going to be 3 plus 2, so that's 5. 5 minus 2, that's 3. So now this loop is going to create the sum xi third or cubed sum, right? And after it creates that, now we have A32 and A23. So 32 is going to be here, and 23 is going to be here. So now we created those two sums. So now you can see that we have two sums remaining, which is this one here and this one down here. Now for the third j, we can see that it's going to be 3 plus 3 is 6. 6 minus 2, that's 4. You can see that this is going to create the xi to the fourth sum. And now that's going to be A33, and A33 is equal to sum. So it creates this sum. And after we break out of this loop, now I is 3, right? So 3 minus 1, that's 2. So that's going to be I or y minus x to the power of 2. And you can see that this loop is going to create this sum that we have down here. And it's going to be B3 is equal to sum. Now, this took a while to explain, but this is basically the meat of the code. So you can see how this code, going through all these loops, created the A matrix here and the B vector. And given that I have the A matrix and the B vector, and this is a code that I've explained in prior lessons, now we can get the solutions. In this case, the solutions are A0, A1, and A2. And those are going to be stored in the vector Si. So S1 is going to be A0, S2 is going to be A1, and S3 is going to be A2. So now, based on this theory, now we created this matrix and solved it. So now we have the best fit line that basically has the minimum sum of the square of the residuals. So now let's actually quantify the effectiveness of our model. So quantifying the effectiveness of our model is by calculating the R squared. Okay, so if you remember, R squared is calculated by ST minus SR divided by ST. Now ST is a sum error, basically, but it is related to the average Y instead of related to the model that we created. Okay, so if you remember with B1 here is the sum of the Y. So the average Y is basically the number that I have stored in B1 divided by N, right? So we initialize ST and we create this loop to create the sum by making sure that we subtract the yi from the average. So this loop creates us the ST. Now with the SR is slightly more involved because we have a lot of terms here. So let's actually go through this. So for I is equal to 1 to n, so basically we're going to go through all 20 points. So let's take the first point. So the first point, y of I. So we're going to take the first point. So it's going to be j is equal to 1 to o plus 1. So we're going to loop 3 times. And we're going to see why we're going to loop 3 times. So this is the first point, y of I minus. Now, the j for the first j is 1. So 1 minus 1, that's 0, which means this term is equal to 1, which means it's going to be y of I, or y of 1, minus s of 1. So y of 1 minus s of 1, so y of 1 minus a naught, right? So we can see here, y of 1 minus a naught, right? So we go to the second loop, you can find j is 2. So if j is 2, this is x to the power 1, and this is going to be s of 2. So s of 2, we have a1 stored in it. So it's going to be sum minus a1x, right? So you can see we subtracted this part 2, minus a1x. And you can predict for the third loop, we have when j is 3, so it's going to subtract, it's going to take the sum, subtract s of 3 multiplied by x I to the power 2, right? So basically subtract this term. And we're going to do this for all the points, right? So we're going to take the second point, y of I minus, the first loop is going to subtract a naught, second loop is going to subtract a1 xi, the third loop is going to subtract a2 xi squared, and it's going to loop and do that. And as it does that, it makes sure to add this to this sum of which we're trying to create, SR. Given that is done, so now we have enough information to get R squared. So R squared is ST minus SR divided by ST. Okay, so this is just a display code that outputs the vector S in those 3 cells that we have here. So this is S1, S2, S3, which is analogous to A0, A1, and A2. And also it displays the R squared here. So let's actually go ahead and run the code. So here, when you're using this code, normally you will say, okay, so we have 20 points here, and I have a second order polynomial. And again, this code can still be used for the previous lesson that we dealt with, the linear polynomial, by just changing this into 1, and it's going to output the only the A0 and A1 for you. So I'm going to put it 2. And I'm going to run the code. All right, perfect. So we have the intercept is about 4.563. So if we extrapolate here, it's going to be 4.563. We have a slope of 2.06. We have A2 of 2.389. And we have an R squared of 0.9604. So basically 96, so this model explains 96.04% of the behavior of the data points that we have here. So let's actually go ahead and compare this to Excel's inbuilt function. So I'm going to right click here, and I'm going to add a trend line, and I'm going to use a polynomial of order 2. And I'm going to say display the equation and display the R squared, and I'm going to compare them to the values that I got. So let me enlarge this a little bit. So you can see here we have the A naught is equivalent to 4.5631, exactly what we got here. The A1, 2.062, the same as we have here. Also the same thing for A2. And also exactly the same r squared. And again, like I mentioned in the previous lesson, that is not a surprise because that's the same theory that Excel uses in its own coding by generating this trend line. So let's actually recap what we did in this lesson. So in this lesson, we said that we don't always have points that follow a linear trend. So what if they follow a curved trend? But not only that, what if they follow a polynomial trend? How do we fit a model to that? And we do polynomial regression. We went through this theory of how this is done. We find the best fit term by minimizing the sum of the square of the residuals. We got those three partials, and it ended up to have a 3x3 matrix if I'm dealing with a second order polynomial, right? So before I can solve this 3x3 matrix, I have to create the matrix A, and I have to create the vector B, which is the three values here I have on the right side. And I found those are defined entirely in terms of the data points. N is the number of data points. We have the sum of all the x's, the sum of the xi squared, xi cubed, and the sum of xi fourth, and those three sums I have on the right hand side. Given that I have those vectors, we can apply any system of equation solving technique like Gauss elimination, Gauss-Jordan, LU-DCOM to find the associated solutions A0, A1, and A2, right? And at this point, you will have the best fit curve, but also you want to know the effectiveness of this curve, and you would calculate the r squared. And in this case, this model was pretty good. It explained 96.04% of the behavior of the points that I had laid out here. Okay. So in the coming lesson, so right now we dealt with if we have a straight line, how do we fit a model to that? And how do we fit a set of curved data points if they follow a polynomial trend? What if the curved data points don't follow a polynomial trend? How do we fit a model to that? And that's going to be the topic of the next lesson. Well, that's it for this lesson, and I'll see you in the next lesson.